So this talk, with this talk, I kind of want to bring you to the short trip to internals of EVM. I actually proposed it before, but then I found a tweet that says it's also beneficial for Ethereum devs to know how the lower level works. So yeah, it's on the internet, then it's true, and we can move on. So I work for Ethereum Foundation, but most of my time, for over 5 years, I was actually implementing EVM and like checking what people propose for it for later. And I'm currently in the Epsilon team, which previously were also working on WebAssembly. So yeah, this is where you can find some information about me. And in this talk, I kind of want to split it into two parts. Firstly, like describe how the current EVM work and some historical context for decisions being made for design, and then to show you what are options for the future. So I want to talk about jumps. Like if we zoom out from EVM, the jump instruction in different machines and virtual machines as well is an instruction that allows you to break the in order instruction execution and move it to some other place. So it's kind of the primitive instruction that allows you to build up more sophisticated control flow in your program. And so the best approximation, maybe like intuition to build if you don't know it, is go-to statement in some languages, which is kind of the unconditional version of a jump. And mostly in like many other places, they usually this instruction are referred as branches. We don't do it in EVM. There's small reason for it, but yeah, I will try to show it later as well. So in particular, in EVM, we actually have two instructions. One is conditional jump, and the one is one is unconditional jump, and the conditional variant of it is jump I. So there's nothing. There's not so much to tell about, like to find like a lot of differences comparing to other places. It mostly takes the information from the EVM stack where to go next. And the conditional version does why not to do it based on the additional conditional parameter. But what is important in this context is that we actually take this information from the EVM stack, so that's under the control of the currently program being executed. So that means, and this is the name we kind of refer in at least Ethereum ecosystem, that they are dynamic in the sense the target we're aiming for can be computed during the program execution. And it was desired for a long time to have some kind of static variant of that, because it can be noticed that most of the programs currently actually know the destination during the compilation time. So outside of Ethereum, this like concepts of static and dynamic are actually referred as direct and indirect. And the difference is that the direct jumps gives you much more efficiency because the destination is known much earlier during execution that in the case of indirect jumps. For basic interpreters, doesn't really matter so much. So the simplicity of EVM kind of gave up efficiency and used indirect jumps as the basic block. And the good thing about these are that they are more generic, so you can always emulate the static version. But there's one more thing which is important in the case of EVM internals in terms of control flow. There is like special jump test instruction as well there. So it doesn't do anything useful actually during execution, but it's a kind of marker that for all possible places you can jump to during the EVM execution. Yeah, this is like requirement which is checked at runtime. So whenever you execute a jump instruction, you have to check that destination is a jump test instruction. So it doesn't. So it's more than to be the valid byte. It's actually a bit more complicated to figure out if this byte you're jumping to is actually the jump test instruction. Because we need to kind of also eliminate the immediate values of push instructions. And this jump test instruction wasn't there actually in the beginning. So the like very like old EVM specification, which predates the EVM launch, didn't have it, and you could actually execute any bytes as you want, including the data bytes. And people were happy about that because for like basic interpreter implementation, doesn't really matter. But also before the Ethereum launch, we actually were working on a prototype of translating EVM bytecode to machine code to produce some kind of just-in-time compilation capabilities. And in this project, we were using LVM as an intermediate representation. And to go from EVM bytecode to LLVM IR, it was really difficult to do it with the old spec because LLVM IR is kind of a bit high level than the EVM bytecode, and they have much more restricted branch instructions. So it was mostly incompatible. Then that was the reason, like the main reason we introduced jump test instructions in the first place. And with the jump test instruction, there's also jump test analysis involved. So before any execution, we actually have to scan the whole code and check what are the valid jump test places actually. So mostly we don't want to confuse the bytes that are related to push instructions with the actual jump test instructions. Therefore, we need to kind of skip the data sections and also like note the final result of the analysis somewhere. That actually turns out to be rather costly because it's proportional to the code length statically, in the sense that even if you don't execute all of the code, you need to still analyze all of it. And for deployed code, it's not so big deal because you can always keep because the code is immutable, and therefore you can keep the analysis result together with the code. But this turns out to be a bit problematic for init code, which constructs new contracts. And therefore, we kind of try to mitigate this issue with the new AP that should be included in the next upgrade. So the new AP mostly adds some limits to like what the length of init code can be and applies some additional gas cost per length of it. So like the reason for jump test to exist was a bit different, but it makes some, I think, positive outcome in the current world is that the EVM bytecode is more predictable from the static analysis. So there's no like hidden instructions somewhere in the data that you could be able to execute if this mechanism is not in place. So I think, many people would agree that executing your data in your application is not the thing you really want to have. Yeah, so that was more or less the the thing that like describing how the current EVM works, and I try to quickly show how you can improve that. So if we kind of see like what kind of control flow primitives many other places have. So mostly they have, as I mentioned, direct and indirect jumps, and there's also some which mostly operate on this function on subroutine levels, and then outside, if you want to combine different subroutines, there are kind of similar concepts for calling functions. So I actually checked like what is the status, and usually in everything like intermediate representations and existing machines, like all of them is somehow covered. We don't want to like go into details how they work and like that, but mostly have to trust me that they have like equivalent representation in all of these. And with the EVM, we just have this, right? So we just have like indirect jumps, which works for all of these purposes, including splitting code into functions and calling functions. And it's even worse. That's why. So it's mostly like matching like the machine level code, where you actually take the target as a kind of on-stack value, while the intermediate representations have more sophisticated instructions that actually have much more restrictions. That was the reason for the jump test. And I mean, how can we change the landscape of that? So the usual usual theme right now is to use EOF for that. So this is kind of the same thing for this case. So EOF is a new proposal to actually put some additional structure to the EVM bytecode. Some of that was presented yesterday by Alex, but not going into details. It's a kind of extendable and versioned container for EVM bytecode, and in this case, it actually allows us to have instructions with additional immediate bytes following, which was not possible previously due to backward compatibility reasons. And if you want to learn more about like to find a primer for EOF, the link in the end is probably the best place to start with. And with that, we actually related to EOF. We have two different existing proposals how to change the control flow in EVM. So firstly, we can implement in direct jumps or static jumps, as they called in EVM world. So this is kind of simple. You just put the target you want to jump to as an immediate value, so it's guaranteed to be constant, and there's not so much different from the current implementation. On the other part of the missing instructions, we also propose to have some kind of subroutines or functions presence in EVM by splitting the code physically into different sections, and then have special instructions to go between these sections. So this is represented by EOF functions proposal with call F and read F instructions added. And what is not a mistake here, I'm actually considering removing the previous jumps. So the usefulness of static jumps combined with calls, it's actually pretty, like, it's filling almost all of the space. Currently, Solidity doesn't need anything besides that. The only thing where Solidity is using jumps that are not using constant values right now is to emulate internal functions, so kind of the functions present in that. So I haven't found competing arguments to include other instructions, but there are some ideas how to do it if they are needed. So there's kind of in-place jump table instruction that can be used, and also we can have some kind of indirect behavior for calling. It's technically it's not difficult to implement these. The question remains if they actually provide some useful cases. Yeah, so that's all I had, and if there are any questions, I'm happy to answer this.
Thank you very much. Thank you indeed. We have some time for questions, so if everyone has any question, feel free to raise your hand and I will run.
Thank you for your talk. How would you describe your reasoning of constraining jump targets in terms of scoping functions to limit the jump targets to a specific or secure set of targets?
So if I understand, like, what is the reason to partition the code into separate sections, right?
Because no, my question is way more open. Like, what are your thoughts? What is your reasoning behind the constraint set that you implement to limit jump targets?
So mostly what is enables that's the main driving factor. Maybe I start with nice thing is that you give you some compatibility with existing intermediate representations, so you can do crazy things like translating different low-level codes between different formats. But that's not the main reason. The main reason is that when you have restricted control flow, you can put much more analysis up front, and some of that we want to actually bring to the consensus layer. So we can validate codes to be deployed to the blockchain up front, which eliminates a lot of checks at runtime. So we can actually, for example, check if the given subroutine will not underflow the stack, which means all the deployed code for subroutines on the blockchain will be guaranteed to have this property. Then we don't have to check it at runtime.
Thank you. Any other question? Hands up.
Hi, so maybe a follow-up to this question. I was wondering, so you said basically for direct jumps, you don't need to, you can check at deploy time or at compile time,
yeah.
Right? For indirect, it's a problem, and then you have the jump test. What happens if they want to implement the indirect call? What kind of measures would you put in place to check that an indirect call cannot jump anywhere?
Oh, so for direct call, right? Did I get it right?
So yeah, I would guess direct call is okay. Indirect call, I guess, is right?
So yeah, that's kind of probably the last point. We didn't put a lot of kind of design yet, but my kind of understanding would be that you would need to put some subroutine identifier there. And the simplest way is just to enumerate the subroutines from 0 to use some index, and then it would be up to EVM responsibility to check if the identifier is actually correct. There might be some extensions to that, like for example, number of parameters subroutine takes if it matches the current thing. And one extension I also have in mind is that we might want to have different identifiers. So if you see current external functions for I don't know, mostly in ABI encoding for Solidity, they use 4-byte identifiers. So maybe if we actually allow 4-byte identifiers there with not ordered things, then that would also simplify dispatch for Solidity. So it's kind of still on napkin design, but we're thinking about that a bit.
Thank you very much. Time for one more question. Raise your hand. We got one.
Thanks. In just general, is there any drawbacks with the direct jump and direct call mechanisms you're proposing?
Well, there are some things. So, like on the main, we need like on the low level, we need to make some like design decisions. Except like one of these was to like use simple 2 bytes integer encoding there. So like reachability is limited to 2 bytes offsets. So like technically there are some like decisions where we prefer simplicity over like completeness in this sense. And from higher level, so I think I don't see much problems with it, except for the cases we need this like 2 other more rarely used instructions, but that could benefit. So far, as we checked Solidity code generation, they actually don't use any of these missing 2s, but maybe there will be, some desire to have it, maybe for other languages, maybe for Solidity itself at some point. So, yeah, I think if we have all of these 4, with good reasons to have them, I don't think there will be some gaps in the design then.
Thank you very much. Grand round of applause for Pavel.